Hi, everyone, and welcome back. It's Kira Garfola with Greenville Tech's Math 109. Today, we're going to talk about section 5.1, which details exponential functions. So to get into exponential functions, we first need to review some properties of exponents. You've probably learned about these properties in previous algebra classes, but they're going to be crucial for you to understand and succeed in this chapter. So the first rule that we're going to refresh is a to the m times a to the n. And remember that that's going to equal a to the m plus n. So here, if we have the same base, so a is the same in each of them, and we're just raising them to different exponents here, the exponents simply add. For example, if we have 3 to the third times 3 to the second, then it's really just going to be the same as 3 to the 3 plus 2, which is 3 to the fifth, which is 243. You can certainly check this out and verify yourself by typing this in first and then typing this into your calculator, and you'll get 243 for both of them. Another one is that a to the m divided by a to the n is a to the m minus n. So now instead of adding, we're subtracting because we're dividing. An example there is 4 to the fifth divided by 4 to the third. That's going to be the same thing as 4 squared because 5 minus 3 is 2. Which is going to give us 16. Again, you can use your calculator to verify, but it's going to definitely save us some time when we're working with the algebra. A few more properties that we can look at. Remember that a number to a negative exponent is 1 divided by that number to the positive version. So a to the negative n is the same as 1 over a to the n. You can also further separate that as 1 over a in parentheses, all of that raised to the n. Because remember that 1 raised to any number is still going to be 1. So for example, if we have 2 to the negative 4, that's the same as 1 divided by 2 to the 4, which is the same thing as 1/2 to the 4th, which all comes out to be 1/16. Sometimes it makes more sense to leave it like this, and sometimes it makes it more sense to leave it like this. A number raised to the 0th power is always going to be 1. So a to the 0 equals 1. This is going to be true for any value of a that is not equal to 0. 0 to the 0th is actually an undefined number. It's something that if you move on and take calculus, eventually you'll talk about limits and you can look at that. But this is actually undefined here, but we won't see that too much in our class. Any number, so 1,783,202 is still going to be equal to 1, okay? So here if we have that whole quantity of 5x squared plus 4x plus 13 to the 0, that's going to equal 1 because it doesn't matter what those are, it's going to equal 1. Then we have a quantity, a times b, so a product, a times b, raised to the n. Remember that that n is going to distribute here. So it's going to be a to the n times b to the n to simplify there. Again, remember that the power distributes. So if we have 2x to the 4th, oh my goodness, there's a typo here. This should be 2x quantity to the 4th, right here. It'll be 2 to the 4th times x to the 4th. In fact, let me fix that right now. Of course, it's being difficult today. Okay, now we have that fixed. Okay, sorry about that, guys. Don't want to cause any confusion. So 2x quantity to the 4th, that 4 distributes to the 2, and the 4 distributes to the x. So you have 2 to the 4th times x to the 4th. 2 to the 4th is actually 16, so you have 16x to the 4th. Make sure you can practice these and you're familiar with them because they will make your life easier here. Another property is if we have a over b, so two numbers, a over b, all of that raised to the n, then our exponent just distributes. So we'd have a to the n over b to the n. This is very much related to that negative exponent that we talked about. Remember, 1 over 2 to the 4th is the same as 1/2 to the 4th. It's the same thing here. So here, if we have 2 over x quantity to the 3rd, that's 2 to the 3rd over x to the 3rd, which would just give us 8 divided by x to the 3rd. Now, if we have a to the m, all of that raised to the n, if we're taking something that's raised to a power and raising it to a power, then our power is actually multiplying. So here we would have a to the m times n. So for example, if we have 2 to the 3rd raised to the 2nd, this is going to be 2 to the 6th, which is 64. You can show this with a calculator because 2 to the 3rd is 8. Raised to the 2nd, 8 squared is going to be 64. Okay, so take a few moments, review those. If you need some extra practice in your textbook, there's the algebra toolbox before chapter 5, and that goes through a lot of these. There's a lot of extra practice problems there, so you can get refamiliarize yourself with those. Definitely take the time and get the practice if you need it, because it is going to be important, like I said. So now we're ready to dive into Unit 3. We're going to talk about exponential functions. So an exponential function is just a function of the form f of x equals a to the x, where here a has to be greater than 0 and a cannot be equal to 1, because 1 to the x wouldn't be very meaningful. It would just be a horizontal line equal to 1, right? A here is what we call the base of the function. So whatever we're raising to the x power is going to be our base. Now notice here, this is different from what we've seen previously with power functions, right? Power functions, x was down here in our base. Now we just have a number raised to the x power. Our variable is actually up here in the power. So that's going to be your big difference here. So let's talk about graphing an exponential function first. Let's start with a pretty simple example of y equals 2 to the x. So 2 is our base here, and it's going to raise to the x. I find it easiest, and I've been doing this for a long time, I still make a table of values when I'm graphing these. So to do this, I can set all kinds of different x values. So let's look from -3 to 3, for example, and let's look at f of x. So we have 1/8, 1/4, 1/2, 1, 2, 4, and 8. Again, 2 to the -3 is the same as 1 over 2 to the 3, so that's 1/8, and so on for each of these. If we want to graph these, we're just going to graph each of these coordinate points, and we're going to connect them with a smooth line. And we're going to see a graph like this. Now you can see that this is anything but linear, right? And it's not really a quadratic like we saw before. This is an exponential function. It starts small and it grows rapidly because it's raising to a different power each time. Now in our earlier example, we had a, what was a here? A was 2. If a had been less than 1, so if a had been a fraction, for example, then our graph would actually, instead of climbing exponentially, it would drop exponentially. So it would start really tall and it would drop off and it would come down here. And you can think about this as if a was a half, for example, so 0.5. Remember that 0.5 squared is going to be even smaller than 0.5 because you're going to take a half of a half. And if you do that again, you'll take a half of a half of a half, and a half of a half and a half and a half. So as x grows, it's actually going to shrink down here. Whereas when x is to the -2, for example, the 1/2 to the -2 would be the same as 2 squared, which would be 4. So since it's a fraction, it actually starts the smaller, the further negative we go on x, the higher our number is. Whereas the larger we go on x, the smaller it is. If that doesn't make sense, make a table of values and take a look at that phenomenon. Now, if a is greater than 1, our graph is going to look like this, like what we just saw. So if we have an a of 2, like our earlier example, then 2 to the first is 2, and 2 to the second is going to give us 4, and so on, okay? And when we get smaller, remember if we have 2 to the -5, that's 1 over 2 to the 5. Okay, so that's going to be 1 over 2 to the 32nd, I believe. And so, or it's going to be 1 over 30 seconds. So it will be very small and it'll be close to 0. So again, that table of values can help you see which way it goes. Notice here that all of our graphs, even in the previous example, went through 0, 1. And that's because any number to the 0th power is going to be 1. So these exponential functions should always grow, assuming there are no other transformations. They should always go through 0, 1. Now, as I just mentioned, we can do transformations on exponential graphs, just the way that we did them in the previous unit, okay? I believe it was chapter 4 that we covered transformations. So, for example, if we have f of x equals 3 to the x minus 2, notice that this minus 2 is partnered up with the x. We can actually have little parentheses right here. Okay, so that's going to mean that we have a horizontal shift. Since it's minus 2, it's going to move it to the right. And so our parent function is 3 to the x, and it's going to shift 2 units right. And if we look here, we can see that this dotted line is the original function. It goes through 0, 1. And here, when we have 3 to the x minus 2, it's the same shape. It's just going to shift 2 units over here. So instead of hitting here, everything that was here is just going to go 2 units over. So 1, 2, 1, 2, and so on. It just shifts that horizontal to the right. Now you give it a try. Go ahead and pause your video, give it a few minutes, and tell me what is going to happen to this graph. When you're ready for the solution, there's a couple things that we can note. Here, our base is 1/2, so we know that we're going to have that opposite shape, right? We're going to have it falling, not inclining, because it's between 0 and 1. We see this negative out here, so we know that it's going to have a reflection. And we see this x plus 3 up here, so we know that we're going to have a horizontal shift. There's no plus or minus out here of everything, so it's not going to vertically shift, but it is going to shift to the left by 3 because of this plus 3, and it's going to reflect over that x-axis because it's going to be negative in front of it. So again, our parent function is 1/2 to the x. It's going to reflect across that x-axis because of this negative, and it's going to shift left 3 units because of this x plus 3. If we look at the graph, again, the dotted line is our parent function here, and our final product with the transformations is here. So we flipped it over, and then we shift it to the left. If you're graphing these without a calculator, again, I would highly encourage you to plot a few points because it's really hard. It's hard enough to visualize with linear functions, right? It's really tricky to visualize and just kind of freehand sketch, at least for me, if we're dealing with exponentials. Now, previously we had talked about, the vertical and horizontal shifts, and we used to talk about vertical compression and stretch. We can also talk about horizontal stretch and compression here, which is similar but slightly different. So if we have f of a times x, so anywhere we see an x, we're multiplying it times a, we are going to horizontally stretch or compress it. If our a is greater than 1, we are horizontally compressing it, so it becomes narrower. If a is between 0 and 1, then it's horizontally stretched and it becomes wider. Now be careful here, because a bigger a means that you're compressing more, and a smaller a means that you're stretching. So it kind of goes against that intuition, right? With vertical, if it was big, then it stretched, and if it was small, it compressed. But here we're kind of going opposite. And you can think about this in terms of that vertical stretch and compression. Okay. If you have a horizontal compression, it's narrower. So it's going to be similar to a vertical stretch. Again, be careful here. A large A is a bigger compression. A smaller a between 0 and 1 is going to be a more stretched out graph. Again, plot points to make this make sense. If you're not sure, always plot some points or graph it on your calculator or do something to look. You'll always have your calculator on the test. So use your calculator, pause the video, do what you need to do to graph our parent function of 3 to the x, and then look at what happens when you have 3 to the 2x, and then look at what happens when you have 3 to the 1/2 x or 3 to the 0.5x. Again, pause it, and when you're ready to move on, unpause, and we'll talk about the graph. looking here, we see all three graphs on the same. Our parent function, 3 to the x, is this black dotted line here. Now the blue line is our y equals 3 to the 2x. So here, even though we had 2x, it was 2 here, we had that horizontal shrink, okay, that horizontal compression. So it got narrower. It shrunk up. Instead of spreading out all the way over here, it pushed up and shrunk up. Now, when we had 3 to the 1/2 x, we horizontally stretched out. So we went further out on the x-axis. So it didn't climb quite as fast. You can think about this as kind of a little bit backwards from the vertical case. When it was 1/2 x, it stretched out. When it was 2x, it compressed. Now, putting all of this together, we can talk about exponential growth and exponential decay. So a function exhibits exponential growth if we can write it as a function, f of x equals a times b to the kx. Now, that looks like a lot of numbers, but really only a couple things are going to change between these. So a is just a coefficient here, and it has to be greater than 0 for this example. K is a constant on x, and it has to be greater than 0. And b, our base here, has to be greater than 1. That is the key to exponential growth, okay? B here has to be greater than 1. Remember, we talked a few slides back, we talked about if the base was less than, or was between 0 and 1, or less than 1, and then we talked about the base being greater than 1, then we had that case where if it was less than 1, it shrunk, and if it was greater than 1, it rapidly grew. And exponential growth is where it's rapidly growing. So our base has to be at least 1. Whatever is raised to the power has to be at least 1, has to be greater than 1, okay? You want to look for keywords when you're modeling these, like it grows exponentially, or it increases exponentially, or it grows at an exponential rate. Something like that. You're looking for keywords of growing or increasing. We actually see exponential growth a lot of times in the real world. So this is very applicable to things outside of just a math class. Let's look at an example. So suppose inflation is predicted to grow exponentially by 4% each year. So this means that an item that is $100 this year will cost 100 times 1.04 next year. And every year after, it's going to continue to multiply that final answer by 1.04. So we're going to get that 1.04 because 100% is times 1, and that 0.04 accounts for that 4% growth. So we can actually write a function to describe the cost of an item after t years. Okay, because we know that it's going to multiply times 1.04 every year. So our function is f of t equals 5,000 times 1.04t. 5,000 goes out front because we're talking about the number 5,000, just like we talked about 100 up here. And then 1.04 is our growth factor, and it's going to go to the t. So after 1 year, it'll be 5,000 times 1.04. After 5 years, it'll be 5,000 times 1.04 to the 5th, and so on. Remember your order of operations here. Remember to apply the exponents first and then multiply. Now, from our previous answer, how much would we expect the item to cost after 12 years? Remember that our previous answer was the model 5,000 times 1.04 to the t, and we're asking how much it'll cost after 12 years. So we just need to plug 12 into here. Doing that, we see that that item will actually cost $8,005.16. That's a lot after 12 years, right? It's growing exponentially. It grew really fast at a 4% rate. Now, on the other hand, we have something called exponential decay. And this is kind of the opposite of exponential growth, okay? So we're still writing it as f of x equals a times b to the kx. We still have a is greater than 0. We still have k is greater than 0. But now b is between 0 and 1. Notice this is the only thing that changed between exponential growth and exponential decay was the value of b. All the other requirements were the same. Now, instead of having b is greater than 1, we have a fraction or a decimal value for b. So b is between 0 and 1. And remember that when we raise a fraction to a higher and higher level, we're actually shrinking it. So that's what causes that exponential decay. You're looking for keywords here like decays exponentially, or falls exponentially, or decreases exponentially, or it's reducing at an exponential rate, something like that. You're looking for that direction of negative, and you're looking for the term exponential. This is also quite common in real world phenomena, so it's kind of cool to get that real world access. Half-life is one of the big examples, especially if you are one of my biology students or the sciencey students. You may understand and have seen half-life before, and this is where it comes from. It's an exponential decay problem. So if we have an exponentially decaying substance, then the half-life is just the time it takes for it to go from what it started as to half of it being left. So half of it has decayed at the half-life. The formula for half-life here, and again, you would be given the formula on a test, would be that P naught is going to be the original amount. Our function P of T is how we're going to model the amount remaining after T years. And K is going to be the half-life that would be given in years. So that means that we can model our half-life here. We can model that amount by what we started with, P naught, times 1/2, because we're talking about the half-life, to the how many years we have divided by what that half-life is. Again, the formula would be given to you, so don't panic and try to memorize the formula, but you do need to understand how to use it. Let's look at an example. So let's say there were originally 0.03 grams of radiocarbon in a dinosaur fossil. The half-life of radiocarbon we know is 5730, so 5,730 years. After 10,000 years, we want to know how much radiocarbon is going to be left in that fossil. So remember our formula for half-life here, okay? P naught is our original amount. So we started with 0.03, so that's going to be P naught. 1/2 stays the same. And we want to know after 10,000 years. So T is 10,000 and K is just our half-life, so 5730. We set it up just like this. Here's our original amount. Here's how much time. Here's the half-life. When we plug all that into a calculator, we get 0.00895. So after 10,000 years, only 0.00895 grams of the original 0.03 grams are left. This is the basis of carbon dating. This is how we know how old fossils are, or rocks are, or anything. Well, I guess not rocks with carbon dating because it has to be an organic material. But we don't just do this with carbon. There are lots of radioactive substances that exhibit this behavior, and we can date all kinds of things using our exponential decay models. Other things grow exponentially. We already saw the inflation example before. You can have investments growing. Lots of things use the exponential model. So it's definitely something that's pertinent in real life and something that you may want to certainly be comfortable with. This is a preview and something you're going to see in your homework. The number E starts to come up, and we're going to use it more and more as we go forward, but we're just going to barely hit on it here. And the number E is just an irrational constant, and it's approximately 2.71828, okay? You guys all know from previous math classes pi, right? E is just similar to pi. Pi is what, 3.14, blah, blah, blah. E is 2.71828, blah, 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 okay? There is a button on your calculator. Every calculator has one that is E, and it's sometimes EXP, okay? And that is just going to be our constant here. Okay, you can use the button on your calculator. You can also estimate it with that 2.71828. Do not estimate it with 2.72. Make sure you carry at least this many decimal places to get the right answer. Otherwise, you're going to encounter rounding error. We're going to use this in a variety of applications. It's used a lot in business. It's used in biology. I'm a statistician, as you guys know. I use E all the time in statistical models. So it's kind of everywhere. It is going to become more important in future sections, but you will see it through the homework here so that you can get an idea what you're going to be dealing with and get comfortable with it. So in conclusion, remember the exponentials, the functions are pretty different than what we've seen before. They're very different than linear functions, and they're different from those power functions because remember, x is actually in your exponent now. We can have exponential growth and we can have exponential decay. It just kind of depends on what your base is and what the coefficients you have in the exponents. And when you want to look at the transformations in the graphs, it's going to work very similarly to what we saw. We added horizontal stretching and compressing to our toolbox, but really that's everything else is the same as far as vertical shifts, horizontal shifts, things like that. Make sure that you practice, practice, practice. In my opinion, the last few sections are harder than these upcoming few sections, but it might just be because I practice them more, just in my day-to-day work, I guess. But don't let yourself fall behind. We're starting a new unit with this chapter. And so make sure that you are able to catch up. Remember, there's all kinds of resources for you in Blackboard. You have my office hours, you have the Math Center, and you have all kinds of other resources. So if you need more help, reach out. Otherwise, I hope to see you guys next time. Thanks for listening, and have a great day.